Waves 2. As always, if you enjoy this content, give us a like and subscribe. So we're going to start Waves 2 with discussing the Doppler effect. And I'm first going to do the definition, which is a little complicated, and then I'll give you many examples of this so you get a better sense of how it works. And the first part is that it is a shift in frequency. Now, with frequency, if we're talking about sound, we're talking about pitch. So we're talking about high frequency and low frequency waves. So it's going to shift from a higher frequency to a lower frequency. If we're talking about light, that might be a shift from blue light to red light, from higher frequency to lower. It could even be from gamma to radio waves. So any shift that's going from high frequency to lower frequency. So it's a shift in frequency of a wave, and remember, that means it could be any type of wave, longitudinal or transverse, due to relative motion between the source and observer. This relative motion means that the source could be moving or the observer could be moving, but as long as one is moving relative to the other, we get a Doppler effect. So this occurs for all types of waves. So this includes transverse, so all of the electromagnetic spectrum, and longitudinal, which means that this also happens for sound. So, for example, if we have a siren that is producing sound, so here's our longitudinal waves that are coming out, and we have a person that's moving relative to the source. This person is going to collide with this sound wave, and they're going to hit these waves with a higher frequency as they approach and a lower frequency as they move on to this other side. But the more common way that this happens is when the source of the wave is doing the moving. So here we have a person standing still. As the wave source moves, the wave fronts, the fronts or the crests of the waves are going to get compressed. That's going to be higher frequency waves, and behind the source, they're going to spread out. So this siren in this case is moving in this direction, so we get the scrunch up on this side and the spreading out on the other side. But this can also happen for light waves. For example, let's say we have a star. The star is producing white light. As it moves towards the observer, the front end of the transverse wave gets compressed. The crests get closer together, so we have higher frequency. And behind, the wave gets spread out. That would be a lower frequency. So if you imagine taking a rock and dropping it into a pond, you can picture that we'll get ripples that will move outward like that. So it'll look sort of like this. And the ripples that you're seeing, these points right here, these are actually the crests of the wave. And the spots that are down below, because we looked at this from the side, there's our curvature. The crests are the lines that we see, and then the section in between we can represent with dotted lines. Those would be where our troughs are. So these dotted lines that would go all the way around would represent the troughs. But what happens if this rock that's dropped in, that's our source, was actually moving to the right? Well, in that case, what we would get would be something that looks like this. And you can see that these are bunched up. I'm not going to continue to draw the circles, but I'm just going to draw the front edge of that, which is going to look like this. So in this side of the wave, like we saw before with the siren, if someone is standing here, they're getting hit with the waves more frequently, and if they're standing back here, they're getting hit by the waves less frequently. So this person experiences a higher frequency, and the wavelength, the crest-to-crest distance, is shorter. On this side, the person experiences a lower frequency, but the waves are more spread out, so the wavelength is larger. But with one large and the other small, we get a set velocity. And that velocity is the same on both sides because the medium has not changed, and it's the medium that determines the speed of the wave. When you hear the Doppler effect, you're actually hearing two different things. So let's say we have a car that's approaching us and then receding from us. When the car is far away, we can't hear the sound very loudly. So the loudness starts very low. And as the car gets closer to us, it gets louder and louder until it passes us. Then it gets softer and softer. That increase in loudness and then decrease in loudness is the amplitude. So that's actually not the Doppler effect, but you do hear that difference. The Doppler effect is the shift in frequency, and as it is approaching, it's a high frequency, but that high frequency is constant. So as it is approaching, the frequency is not going up. I'll say that again because it's important. As the car approaches, the frequency does not go up. The pitch is the same. And as soon as it passes, that frequency drops and becomes low. And the same thing on this other side of this graph. The frequency is low, but it is constant. It's the amplitude that's going up and down. The frequency is high and only decreasing. So those two things you have to listen for when you're listening to a car that's passing you. We can hear the Doppler effect in our everyday lives, but it's harder to understand the idea of light waves undergoing a Doppler effect. And the way it works is this. First, we need to say which end of the spectrum is the higher frequency end. So in Roy G. Biv, the blue or violet end of the spectrum is our higher frequency side, so we call that the blue end, but it could also be called the violet end, but usually it's just called blue. And on the other side, the red end, that's our low frequency side. So if this is our light source, this could be a star, as it approaches this person, they end up seeing a higher frequency. So this is called a blue shift because it's shifted to the higher frequency side. The person on this side experiences a lower frequency, and this is called a red shift. And this has been used by astronomers to figure out whether stars are approaching us or receding from us. And here's how they do it. They use a diffraction grating. The diffraction grating separates out the light spectrum. So if you're looking at a star with particular gases, you'll see these strips of color. So if you see a band of red, a band of blue, and a band of violet, that's from a star that is stationary. So we just look at a star, it's not moving, it could be our sun, and we see this particular pattern. Some people describe it as the fingerprint of a star. Then if we see that this has shifted, so that the red has shifted to infrared, the blue has shifted to green, and the violet has shifted to blue. We've seen all of these shift to the red end of the spectrum. So this is where we have our red shift. And that's how we know that the star is moving away or is receding from us. But if we see the opposite effect, if we see the red shift to orange, the blue shifts to violet, and the violet shifts to ultraviolet. In that case, that's our blue shift, and that tells us that the star is approaching.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Other examples of the Doppler effect are Doppler radar, and this is when satellites are used to determine whether or not a cloud mass is moving towards or away. And that's how, when you see the Doppler radar, we know whether storms are approaching or receding. And also police use police radar to find out if a car is approaching, and not just approaching, but how fast it's approaching. And that's how they catch you speeding. Another example of the Doppler effect, and this is not exactly the Doppler effect, it's a later effect of it, which is the sonic boom. So if a jet is flying really, really fast, what can happen is it gets scrunched up in the front, but they can scrunch up so much that when the jet is going at the speed of sound, the waves start to pile on top of each other, and that creates superposition. So we have all of the crests piling up on top of each other, and we have all of the troughs piling up on top of each other. And what happens when we have this piling up? That's superposition. We add the amplitudes. So if all the crests are on top of each other and all the troughs are on top of each other, we get this giant crest and this giant trough. And what is this? This is called a sonic boom. Another example of a sonic boom is the crack of a whip. The reason that a whip makes that cracking noise is because the tip of the whip is traveling so fast it's exceeding the speed of sound. So what happens if we have two waves and these waves are approaching each other and start to interfere? Well, if the two waves traveling in the same medium interfere and they have the same wavelength, frequency, period, and amplitude, you get something called a standing wave. This is a kind of a tricky concept, but if you think about it this way, when the two troughs hit each other, we'll get a bigger trough. And when the two crests hit each other, we'll get a bigger crest. And when the crest meets a trough, we'll get nothing. It will cancel out. So what ends up happening is you get a giant crest and a giant trough, but because they're equal wavelength and equal amplitude, what will happen is you'll just have these crests and troughs standing still. In other words, they're vibrating up and down, but they're not moving left and right. The waves, the two waves that make up this vibrating wave are moving, but the wave that is produced appears to be standing still. So I will show you a video clip of this because it's kind of hard to see it just on a piece of paper. But what happens is these points are not moving, and the part of the wave here is moving up and down like this. So there are parts of the wave that you need to know. These points right here, these dots that I've drawn, these are called nodes, and nodes are the point on the wave that are not moving. The points that are doing most of the moving, right in the center there, those are called antinodes. So I'm going to put an A there for that, and it's spelled like this. So those are your antinodes. So they might ask you a question. They'll say, here's a standing wave. How many nodes are there? 1, 2, 3, 4. How many antinodes? 1, 2, 3.
The lowest frequency standing wave pattern is this one. It's called mode, M-O-D-E 1, or the first harmonic, or in other words, also called the fundamental mode. It's the lowest frequency mode that you can get in a transverse standing wave. If I double the frequency of that mode, I get the second harmonic, or second mode, and sometimes called the first overtone. And this one, if you'll notice, is going twice as fast as the fundamental mode. It has a node that's exactly halfway between Parker and me.
There are different modes associated with standing waves, and the most basic form that you can get, which actually happens to be the largest wavelength, is called the first harmonic. It's also called the fundamental. So this is our first mode. We have 2 nodes and 1 antinode. And if we think of this as having a large wavelength, we could call this distance L. Then L would only be half of a wavelength. So you could think of this as continuing. Here's our crest, and then our trough would be over here. So our wavelength would be double this distance. So a common question, they might say, L is 3 meters. What's the wavelength? Well, this is only half of a wave. So the full wavelength would be 6 meters. So if we write it this way, we could say V equals, and this would have a very large wavelength. So therefore, it would have a very low frequency. It will oscillate not very quickly. But if we look at the next one, this is called the second harmonic. In music, it's called the first overtone. And this one has 3 nodes and 2 antinodes. And in this one, the length is equal to the wavelength because we have a crest and a trough. So if this distance was 3 meters, then the wavelength would be 3 meters. In this one, we say V equals F lambda. The frequency is going to be a little bit larger because the wavelength is a little bit smaller. So it's going to look like that. Now, if we go on to here, you could probably guess this would be the 3rd harmonic. And in this, we have 1, 2, 3, 4 nodes and 3 antinodes. And this one's a little bit tricky because a wavelength is this distance right here. So we could think we have 2 chunks out of 3. So that would be our length would be 3/2 lambda because we have a wavelength and a half. So in this one, our frequency has gotten even larger and our wavelength has gotten smaller. So what's happening this whole time? As we move from our harmonics, we go from low frequency to higher frequency as our wavelength gets smaller. But what's crucial in all of this is what affects the speed of the wave. How fast is that wave going? Well, V equals F lambda. If F goes up, lambda goes down. And the reverse is true. If frequency goes down, lambda goes up. But the speed of the wave is determined by the medium. So if we're not changing the medium, the velocity stays the same. Another phenomenon that you need to know about is called resonance. And resonance is defined as the effect produced when a vibrating object is forced to vibrate at its natural frequency. So, for example, if you have a wine glass, that object can actually vibrate. It does seem like glass is a solid and that it can't shake, but even solid objects can vibrate. So if you take a wine glass and hit it with a fork, it will make a ringing noise. That's its natural frequency. But if we produce another frequency that is exactly the same as the natural frequency as the wine glass, we can actually use that to force the wine glass to vibrate more. And if we make it vibrate enough, we can actually break it. So making wine glasses break is an example of resonance.
My name's Chase and I live in California, and I'm gonna try to break this wine glass by only my voice. Mom, look. It will never. Mom, I broke it!
You did not.
No. Look it! I did! I broke a glass! I broke a glass, peoples! Woo! Don't, Woody! Look it! I broke the glass.
Stop.
I broke the glass with my voice! Isn't that just crazy? Woo!
To break a wine glass, we use a record player as an amplifier, a frequency generator, a high-speed video camera, and a horn driver. We match the frequency to the resonant frequency of the glass. You can see the rim of the glass shaking as it resonates at the frequency of the horn driver. All we need to do now is turn up the amplitude.
But another thing can happen where if you have wind that starts to blow on a bridge, or people start to march over a bridge and start to make the bridge vibrate at its own natural frequency, then you will make it resonate. So bridges starting to shake are another example of resonance. And then lastly, all instruments work off of the idea of resonance. You are making them vibrate at their natural frequency. You can change the pitch by changing the length of the tube or the length of the string, whether it's a brass instrument or a stringed instrument. But when you force it to vibrate, you are forcing it to resonate at its natural frequency.